Today I'm going to present about my research report for the Hang Mathematics Awards 2023. And my research title is Quantum Computing, Adapting Shor's Algorithm to the Problem of CRT Group Size Finding. Well, we will first talk about some notations that we will use in our report. A big O notation is a way to express the asymptotic time complexity of an algorithm using an expression depending on the size of its input. And now we will talk about some background information. Integer factorization is an interesting problem. It is very simple to produce large semi-primes, as multiplication can be done very quickly. And shown here are some common map multiplication algorithms. However, the inverse problem to factor large semi-primes it is very difficult, and all known algorithms take a superpolynomial time or worse. And this fact is widely relied on in modern cryptography, such as RSA. However, in contrast to these classical algorithms, Shor's algorithm is a very fast quantum algorithm to factor integers, and it can factor integers in polynomial time. So this shows how quantum computers could offer an advantage over classical computers in some problems. To understand quantum computing, we must first understand what is it. In quantum mechanics, we do not have a very specific one single state for a particle, and instead we assign a wave function to it. A wave function assigns a complex number to each possible state of the particles. And the evolution of the wave function through time obeys the Schrödinger equation as shown here. And for n classical bits, we can only store n classical bits of information. But if we use particle states to represent n0 and 1, then they can go into superposition. So it would take 2 to the power n different complex numbers in order to represent n quantum bits completely. And we call quantum bits qubits for short. And if we can control and modify these qubits while changing the Hamiltonian, as shown here, then we can achieve computation. One way to formalize our operations done on these qubits are using the quantum gates. And there are some constraints of the operations, so we can represent them using unitary matrices. And shown here are some common quantum gates that we will use throughout the article and in other quantum computation algorithms too. However, quantum computation is not without its limitations either. We must measure the particle to get an output, and also most importantly, Holyfield's theorem states that we cannot get more than n bits of information back out from n qubits. So we cannot directly use quantum computers to compute on a lot of data and extract them all at once, and we need clever algorithms to derive a speedup from this. Now we will talk about Shor's algorithm. The idea of Shor's algorithm is that the factors of n are related to the group of integers modulo n. And if we have an integer a, we can find its order of a modulo n, and let's call the order be r. So by definition, a to the r power minus 1 is divisible by n. And using the difference of squares formula, we can factor it into two different parts as shown here. And if n does not divide any one of them, then their greatest common divisor would be a non-trivial factor of n. And we would be able to factor integers this way. So if we can find the order of this efficiently, then we can factor integers efficiently too. Naive way to do so would be to just try out all the possible powers of a and modulo n, but there is no apparent pattern to this. For quantum computers, we cannot directly retrieve all of these exponents either. So, and there is an algorithm called quantum phase estimation, or QPE for short, which can find an eigenvalue of a quantum operation efficiently using an eigenvector and the quantum operation itself. So if we can construct a suitable quantum operation for this, we can try to use it to our advantage. And here is a description of QPE. And we first prepare some qubits and then put them through a series of the quantum operation itself. Finally, we put it through our inverse quantum Fourier transform and measure the results. The resulting value would be related to our eigenvalue, which we can use for further processing. Now we need to find a suitable eigenvector to put into the QPE algorithm. We could choose the operator that maps x to ax modulo n. And we have an eigenvector us, which is shown here. if we apply the operator, we can see that it is in fact an eigenvector, and its eigenvalue is the exponential of 2i pi s over r. And as you can see, this eigenvalue is related to the order we want. So if we can get this eigenvalue, then we can find the order this way. However, we can see that this eigenvector needs R itself to be constructed, as there is an effect of R there. However, we have one way to solve this. If we take all possible US for S ranging from 0 to R minus 1 and put the quantum bits in a superposition of all these states, then the resulting state is simply the one state. And the one state is easily constructed. So we can construct the eigenvector this way. And we would be able to avoid the problem. And finally, after the quantum routine, we also have some classical pre- and post-processing that we would need to do in order to actually find our vectors. And they are shown here below. And now we will talk about the topic of interest for our algorithm groups. A group is simply a set of elements S with a binary operations that satisfies the following axioms as shown here. And here are some elementary operations and properties of groups. A weaker form of Lagrange theorem, which is a theorem of groups, states that the order of any subgroup H is an order of the original main group G. And the converse of it is that for any divisor D of the order of G, there exists a subgroup H that has order D. And however, not all groups satisfy this, and we call the groups that do satisfy this would be the converse of Lagrange theorem groups, or CLT groups for short. And now we will talk about how the algorithm works. The idea of this is that we can find the order of G if we can get a bunch of different factors of G, of the order of G. And one way to do this would be to generate random elements in the group G and find the order of the cyclic subgroups generated by by each of these elements. Then by Lagrange theorem, the orders would be the factors of the order of our original group G, and therefore by taking the least common multiple of them, we would be able to get our original order of the group. And we could try to adapt Shor's algorithm to do this for us. The procedure of this is that we first generate random elements in G by combining different generators in the group, and then we adapt Shor's algorithm's quantum subroutine to find the orders of these elements. And finally, with these orders, we find the least common multiple of them, and the result should be close to the order of G with sufficiently many factors. And we can encode the elements in binary. And as the proofs of Shor's algorithm do not rely on any specific properties of the integers, the proof should also carry over for general groups. So when we put our own groups in, they should still work. Now we will carry out an analysis of our new proposed algorithm. For a group contained in Sn, where Sn is the symmetric group of n elements, there would be on the order of n log n executions of the group operation. And if we denote the time complexity of one of the group operation as un, then one run of the quantum routine would take n on the order of n log n un time. And with the greatest common divisor can be found very easily, and the least common multiple can also be found easily this way. So for sufficiently large n, the time needed for the LCM is very small. Now we only have to find how many runs of the quantum routine that we need to run. And we can introduce number vectors for this. A number vector V is just an infinite dimensional vector with non-negative integer elements that correspond to the prime factorization of a number. And using the Hardy-Ramanujan theorem, we can find that the probability of having k different factors of n value, be the LCF of them, be the number itself, is shown here in this expression. And now to get a probability PC of actually finding our order, then we can equate this to PC and solve for k. And we take the Taylor expansion of it as log n tends to 0, and we get this. The dominant term is log x. And so we multiply these two together to get the final runtime. In conclusion, we have found a new algorithm to find the order of groups satisfying the converse of Lagrange theorem. And it is shown that it is better than classical algorithms. Thank you.